All right, so next chapter, we'll see how far we get here. So far, all of the stuff that we've been talking about with rotating bodies have been the bodies rotating around what's called a fixed axle, which means that the body sits there and spins. Okay, it never goes anywhere. But what we want to talk about now is something like a wheel, where that wheel, be it attached to a bike, is actually going to go somewhere. And to talk about that, we are going to confine ourselves to something called smooth rolling. So another way to talk about smooth rolling is rolling without slipping. And rolling without slipping means that only one part of the bike wheel is in contact with the ground at a time. And that part of the bike wheel, indicated by my duct tape down here, is not moving along the surface. It's in contact with the surface, and then it's not. Okay? So one piece of the bike wheel is in contact with the surface at any given time. It doesn't slide along the surface, it's just in contact, and then it stops being in contact as it kind of rolls up or rotates out of the way. So when you watch a wheel going past you, two things are happening. The wheel is rotating, and the center of mass, which is located at the axle, is also doing what? What's the center? What? Not the axle, not the handle. What's the handle doing? I can't go any farther. No, the handle's in front of like my body right now, right? Where's the handle now? It's moving, okay? Well, let's not get into opposite direction. Let's not go there. But so I've got the rotating of the wheel, but I also have the axle moving, or the center of mass moving. Okay? So rolling really has two parts. And so if I want to talk about how much the wheel has moved, so again, we're going to draw our attention to the tape at the bottom here. As the wheel moves through a certain angle, okay, so my tape has moved through a certain angle, about pi over 2, okay. A certain arc length has passed, correct? Okay, and that arc length that has passed actually relates to how far the center of mass has moved, if you think about it. Okay, because the wheel itself has to turn through this quarter of a turn, which means as that has happened, the center of mass has moved by a quarter of a turn as well. So we're back to where we started, with that arc length being equal to r theta, where r is going to be the radius of my bike wheel. And so remember that even though this s is an arc length, it's really the distance that the center of mass has moved. So if I take the derivative of both sides with respect to time, I'm going to get ds dt is going to be r d theta dt, right? Now what's d theta dt going to be? Omega. And ds dt is actually going to be the velocity of the center of mass. And they shouldn't be separate if you think about it. If you think about the wheel turning and only one part of the wheel being in contact with the surface at any time, the distance that the wheel, that piece of the wheel has moved through has to be related to the distance that the center of the mass of the wheel has traveled. Okay? So there's two ways to look at rolling. You can look at rolling as a combination of rotational motion and translational motion, which is what we'll do first. But you can also look at rolling as purely rotational motion, which gets a little tricky, but we need it for something that we're going to do later. Okay? Does everybody have what they need off of here? Okay, so let's talk about rolling as a combination of purely rotational motion and purely translational motion. So the purely rotational part means that I look at my wheel as if it is stationary but rotating around the center of mass. And I can actually say that it's rotating this way, which means that there is some tangential velocities at the top and the bottom. Yes, because my wheel is just spinning around. It's the same tangential velocity everywhere on the wheel as long as it's at the same radius. And then I can also think about my wheel as purely translational motion, which means that all parts of my wheel are moving this way. With some velocity v. Let's see if I can make this work. Just want to move this over a little bit. Okay. And if I add those two motions together vectorially, what do I get for the motion for the center of mass in the middle here? How about for my point up here at the top? 2v. And how about for my point here at the bottom? 0. So this also is important with the whole rolling without slipping thing, because the point down here that's in contact with the ground has no velocity along the ground. It is at rest with respect to the ground. And as we're going to see as this week goes on, there is friction involved with rolling. If there is no friction, there is no rolling. But it's going to be static friction, not kinetic friction, because the wheel isn't moving with respect to the ground. So this is, and I like looking at it this way, adding together my rotational motion to my translational motion and explaining what happens. But like I said, any rolling can also be broken into purely rotational motion. Okay? So we can look at rolling as purely rotational motion, which, like I said, we'll need to come back to. Okay. Pardon me? I think the calculation of kinetic energy for a rolling system. Okay, so here's going to be my wheel. I do have my center of mass here. I've got some point P at the bottom, some point T at the top. And I'm going to let point P down here be my axis of rotation. And then all the points on the wheel make circles around point P at the bottom. So point T up here is the easiest. But I'm going to draw some velocity vectors here, and you're going to be freaked out. So I'm just telling you. Okay? Because remember that the velocity vector is perpendicular to the radius. Because the linear velocity vector is always tangential to the circle. So here's going to be the radius for this point here. So there's going to be my velocity vector. And here's going to be my velocity vector. And here's going to be my velocity vector. And here's going to be my velocity vector. Okay? Because everything's making a circle around this point at the bottom that we're going to call the axis of rotation. And the farther away the point is from the axis of rotation, the bigger that velocity is going to be. Because it still has to make a circle in the same amount of time, but it's farther away and it has to make a bigger circle. Okay. Everybody's brain recovered from that little revelation? Okay. But remember, everything on a rotating object has the same what? Omega. So everything on there has the same omega. So we could actually, for instance, calculate what the velocity was going to be at point T. So VT, how are T and omega, how are V and omega related? Okay, so it's going to be times omega, and then what's my radius for point T? It's the diameter from P to T, and if I assume that it's the same wheel with a radius r, what's that distance going to be? 2r. So the velocity at T is going to be 2 omega r. But if we go back to what we had over here, if this is my omega, V is equal to omega r, right? So this Vt is equal to 2V, right? Because omega r is V. And that's what we got up here. Same wheel, same motion, two different ways of looking at it. Okay? You with me? Or so you think? Well, let's check and see if you're really with me. And do checkpoint 1. Everybody needs a book. If you don't have a book. It's in the first or second section. I don't have a page number, I must say. Priya, what page is it on so we can... 297. Okay. So it says, the rear wheel on a clown's bicycle has twice the radius of the front wheel. A, when the bike is moving, is the linear speed at the very top of the rear wheel greater than, less than, or the same as that of the front wheel? And B, is the angular speed of the rear wheel greater than, less than, or the same as that of the front wheel? So you think about it. All right, so let's talk about this. So the first thing that you should recognize is that the center of mass of the wheels are connected. It's a bike. It has to move together, right? The wheels are going to move, maybe not at the same rate, but the whole bike only has one velocity, if you think about what it is to ride a bike. So the center of mass velocity of wheel 1 has to be equal to the center of mass velocity of wheel 2. That's how the bikes are connected. You can't connect them any other way, right? I have to connect this wheel through the center of mass through the axle. Yes? Okay. So that gives you some information, right? Because how could I rewrite V center of mass? Okay, I can rewrite it as omega r. So I can't assume at this point that the bikes have the same omega, right? The two wheels. So I'm going to call it omega 1, but what's the radius of wheel 1? 2r. And if, well, okay. And then I've got omega 2, and what's the radius of wheel 2? Just r. So what can I do? I can cancel out my r's. So I have that 2 omega 1 is equal to omega 2. No. Well, let's just talk about the angular speed for the mo, because that's what we've got written down here. You did. I know. It's okay. But let's look at what the equation actually tells us, okay? If omega 2 is equal to 2 omega 1, which is going faster, omega 2 or omega 1? Omega 2, right? Smaller wheel, smaller radius. Okay, so the smaller wheel, the front wheel, has to rotate faster, so it has a greater angular speed than the rear wheel, which wasn't the question we were supposed to answer. So the question we were supposed to answer is that the rear wheel has a smaller angular velocity than the front wheel. Okay? Hang on, let's let everybody write this down, and then yes, you may. Okay. Good? Everybody got what they need? Gianni's still writing. Sari's still writing. Priya's still writing, which is fine. You have to translate my handwriting before you can write it down. I get it. Okay, we good? Everybody got what they need? All right, so part A, we're going to let Zoe make a postulation. But we're looking at the tops of the wheels, right? Okay. All right, so what do you think? Sure. No. In our funky little picture, the velocity at the top is twice the velocity of the center of mass. Yes. So why don't you state your argument again, and then we'll talk about it. Okay. Okay, so for the recording, Zoe's argument is that because the center of masses of the bike wheels have to be the same because the bike is moving as a unit, and if the velocity at the top of each wheel is twice the center of mass velocity, then those must be moving at the same linear velocity too, which kind of makes sense because they're kind of like in contact with the road together, whether you're talking about the top or the bottom. But we can also kind of look at this, to get to the right spot, mathematically, okay, which is really kind of the same thing that Zoe was talking about here. So we can say that V1 top, like we said, is equal to velocity center of mass. Which is going to be 2, so wheel 1 is the one in the back, so that's going to be 2, how did I do that? Oh, because it's 2r. It's okay. So the velocity of the center of mass is omega times the radius, which is omega 2r, right? Keep me honest here. So this is going to give us 4 omega r, omega 1. Omega 2 top is again going to be 2v center of mass, and this is Zoe's argument that those center of masses are the same. But remember that V center of mass is going to be omega 2 times that wheel's radius, which is r. But omega 2 is 2 omega 1. So again, we get 4 omega 1r. Okay? We got it both ways? Everybody good? Okay, then I want to do one more thing, and then I'll let you go because I can only do so much of that one thing. Okay? And then I think I have all the reading assignments on the portal, and we don't have lab again for a while. Okay? So what I want to talk about now is the kinetic energy of rolling. Okay? And this is where we're going to talk about rolling as a purely rotational motion. Okay, so I've got my wheel, it's rotating around P, which is going to be my axis of rotation. Okay, so what's our formula for kinetic energy? For purely rotational motion. Okay, and in this case, it's going to be the rotational inertia around point P, because that's where my axis of rotation is. Okay, so if we think back to table 10.10-2, what we really have are a bunch of rotational inertias for a center of mass. And we're talking about objects that are rolling. So if we're talking about a wheel or a disc or a cylinder, that I center of mass is 1/2 mr squared. But I'm not rotating around an axis through the center of mass. I'm rotating through an axis P. So how do I get that? What do I have to use? What's it called? Parallel axis theorem. So I take whatever the rotational inertia is through the center of mass, and what do I add to it? mh squared. And what's h? Yeah, it's the distance between the center of mass and the axis of rotation. And what is that? It's r, right? So this was kind of just an example. If it was a wheel or a disc or a cylinder, the center of mass would be a little bit different if it was a sphere and spheres roll. So we'll leave it as I center of mass. So let's substitute in to our kinetic energy equation. Okay, so I've got my kinetic energy is 1/2 IP omega squared, or 1/2 I center of mass plus mr squared times omega squared. Right? And I can get rid of my parentheses. So I have 1/2 I center of mass omega squared plus 1/2 m r squared omega squared. Yeah, just well, it's more of a it's about the same for a disc or a hoop, I think, or a cylinder, but it's going to be different for a sphere. So in case we're rolling a ball, we want to make sure that we leave ourselves open for that. Okay. But what's this? It is v squared. Which v squared is it though? It's actually the v that's tangent up on the edge of the wheel. But that's equal to the center of mass velocity. So that what I have is 1/2 I center of mass omega squared plus 1/2 m v center of mass squared. And so what I have is a rotational part, 1/2 I omega squared. I have a linear or a translational part. And now what I have is a total kinetic energy for a rolling object. Of mass m and radius r. Okay. And what you're rolling is going to be important because how the mass is distributed affects what I center of mass is. So if I roll a ball down a hill and I roll a hoop down a hill, that split between rotational kinetic energy and translational kinetic energy are going to be different. And we'll explore that on A Day, which is Wednesday. You may go.